Hello, my name is Andy Klump, president of ASH WARE, and I am proud to announce ASH WARE's new eTPU graphical state machine tool, which is part of ASH WARE's new DevTool IDE that integrates code editing and simulation. This is the latest tool in a long line of eTPU, TPU, and CPU simulators and compilers. ASH WARE, development tools since 1994. In part 1 of this video, we will look at Freescale application note AN3769, which documents the CAM and crank functions as state machines. We will create a brand new CAM state machine. We will add states and state transition events. We will add a state conditional that allows the crank function to affect the state transitions of the CAM function. Let's look at Freescale application note AN3769, page 24, which documents the CAM function. Interestingly, it was designed and documented as a state machine. Here's the crank function on page 23, also a state machine. And this is not at all unusual. Over the years, we have noticed that many, if not most, eTPU functions are designed as state machines. And so, this became the inspiration for our new graphical eTPU state machine product. This is ASH WARE's IDE for the eTPU. In this project, there is a crank state machine that has been converted from Freescale's set2 crank function. It also contains Freescale's set2 spark, fuel, and knock functions. Let's close these files. Starting from scratch, let's create a brand new state machine named CAM. Now let's create a state. Notice that when a state is created, code is auto-generated in the cam.c file. Let's move this C file to another panel. Let's change the name of the state to seek. Now let's create 3 more states. Start angle, sync angle, and sync lost. This CAM state machine monitors the input CAM signal. State transitions occur on falling edges of the CAM signal. Specifically, transition detection logic detects each edge, thereby causing a TDLA event, which in turn causes a state transition. Let's configure a state transition from state start angle to state sync angle on a TDL event. Right-click the state and select Properties. Check TDLA to select Action Unit A's transition detection logic event. To cause the TDLA event to result in a state transition to sync angle, select sync angle from the Destination States drop-down menu here. Now let's configure the seek state. The seek state also transitions on a TDLA event. However, it is the crank function which determines whether the seek state simply loops back to itself or goes to the start angle state. A state conditional is used, which we'll add by opening the state machine settings dialogs. We'll call this state conditional crank pause seek. Now we'll change the properties of the seek state. Select both the newly added crank pause seek state conditional along with the TDLA event. If the crank pause seek is a 0 when TDLA event occurs, then let's select a transition to state start angle. However, if crank pause seek is a 1 when the TDLA event occurs, select the loopback to state seek. Let's see how the crank pause seek state conditional is used in the crank function by searching for it using the text search utility. It is being set here in the stall function. It is also being set here in the initialization thread. In this last instance, it is being cleared within the gap verified state code. So the state conditional crank pause seek, which affects state transitions in the CAM function, is actually being written in the crank function, which is running in another channel. Let's take a quick look at how windowing works. Up until match A gets set, here, transition detection is disabled. Match A getting set opens the transition detection window in which a CAM input signal transition can be detected. This window closes here on match B. It is important to note that the window doesn't actually close on match B, but instead, should a transition occur just after the match B, then TDLA will get set. However, if both TDLA and MRLB are set, then the MRLB occurred first, because had TDLA been set first, it would have blocked MRLB. And that subtlety will be important here in a moment. Let's add the transitions to the sync angle state. The state transition causing events are TDLA and MRLB. On just TDLA set, all is good, so loop back to sync angle. However, if just MRLB is set, then go to the sync lost state. The third case is when both MRLB and TDLA are set, and as just mentioned, the MRLB event had to have come first, so this also transitions to the sync lost state. The sync lost state has essentially the same state transition logic as the sync angle state, so I'll quickly add it. By clicking on the state, I can bring up the source code for that state in the C file. Let's add state code to the seek state and to the start angle state and to the sync angle state and to the sync lost state. That concludes part 1 of this video. Part 2 topics include how to handle an event outside of the state machine such that the state machine's state does not change using an asynchronous thread. We'll cover how to put common code into a state that gets executed immediately using jump state. We'll cover how to force the state machine into a specific state at the end of the state using a for state. Lastly, we'll show how to do a normal C function call from within state code. Now let's say the host CPU wants to change some parameters in the function and some eTPU side code is needed to coherently write the data. This is done with an asynchronous thread, which we'll name update window. We'll set it to a thread and assign it to the host service request for, which means that it executes asynchronously and does not affect the state machine state. And we'll add its state code. Now let's say we want to have a common piece of code that executes both at initialization and when a link is received from the crank function. We'll call this state restart. The interesting thing about restart is that when the state finishes executing, we want to force the state machine to the seek state, even though the seek state code has not executed. This is done by selecting for state here. Now let's create the primary initialization thread that handles the host service request 7 from the host CPU. To avoid duplication, we want to execute the restart state code immediately without even waiting for another event at all. This is done by selecting jump state here. Now let's add its state code. Let's add state crank lost sync, which executes on a link from the crank channel. Similar to the initialization thread, this executes the restart state's state code immediately using jump state. Now let's add restart's state code. The last state, which we'll name error, is special. It executes on invalid conditions, that is to say, conditions that would not be expected to occur, such as a thread executing when no thread-causing event is active. But it is good to have these situations steered to code that can say, set a global error flag, thereby making the unexpected error observable. We'll do a jump state to restart. Now let's add its state code. At the top of file cam.c, there is an auto-generated file named cam.h. Let's open it and take a look. There's a spot for adding our own channel variables. Channel variables are stored in the channel frame that is used to store variables private to that specific function. Since each channel has its own channel frame memory, this allows the same function running on different channels to behave differently. For example, this allows several channels to run the spark function, yet the different channels fire their sparks at different times. Let's add the channel variables that have been referenced in the code. Now, it is also possible to have regular C functions that get called from within state code. However, we want these C functions to be able to access the channel variables that were just added. These C functions need to be member functions and declared here. Now let's add this function to the C file. Part 3 of this video covers building the code, running a simulation, tracking which states are running and when, running the simulation to a specific state, measuring a state's execution time, and lastly, stopping the simulation at a state using a breakpoint. Let's build the code. All the C files in the project are rebuilt. I see that there's an error in file cam.c line 38. Click on the error to pop file cam.c and scroll the offending line into view. There is a missing pound define and a couple headers that need to be included. Let's include them at the top of the file and rebuild. Excellent, this time the build is successful, but actually slower than it needed to be because not all the files were actually out of date. Had I selected Make, instead, all file compilations would have been skipped except cam.c. In this make, I see that nothing gets rebuilt since everything is up to date. Okay, let's take a look at the simulation. I right-click the mouse in the right side of the waveform window. Excellent. This top signal, cam, shows the color-coded state enumeration. The first state, which is colored purple, is the restart state. As I hover the mouse over the different states, hint text indicates which state is active in that channel at that time. The states in the cam state machine window have also now become color-coded and match the colors in the cam waveform. If I reset the simulation and select Go to State in the pop-up menu, the simulation runs to the start of that state's code. Additionally, the state code pops into view over here. Note that the auto-generated state prologue code has already executed. It gets created by this cam common prologue code 2 auto-generated tag in the source code. Don't modify this tag because it is used to create the auto-generated prologue. I would note that this prologue has already executed because of the orange color of the code coverage indicator here. Orange indicates that the code associated with this source line has been partially executed. Fully executed code would be white. I reset the simulator and the code coverage indicator changes to black, indicating that the code has not been traversed at all since reset. Let's measure how long the thread that handles the first sync angle state code takes to execute. First, select the cam thread from the Waveform Options dialog. Note that a cam thread executes on every cam state change. I place the left and right cursors around the brown to orange state transitions from state start angle to state sync angle. 2 zoom-in cycles are needed because the thread is fairly short. Using the up or down arrow keys on my keyboard, I'm going to make this the active waveform. The left and right keyboard arrow keys can be used to snap the 2 cursors onto the thread transitions. The delta cursor indicates that the thread time takes 1.275 microseconds to execute, which is fairly quick. Now let's say I want to single step through the sync angle state. I find its state code by clicking on the state. In the cam.c code window, this state code scrolls into view. Next, I place a breakpoint by clicking just over the left edge. Then hit go. The simulation stops at the breakpoint when the state code next begins to execute. I hit step several times and the simulation steps through the code and into function setCamEdge window. That's it for now. Thanks for watching. I could show you a bunch more things, but my boss told me to keep this video under 15 minutes or she would send me down to work in the mines. ASH WARE, embedded tools since 1994.